Hi everyone. Just addressing your feedback from today. Why don't you include liquids in the equilibrium expression, the K equation? There's two reasons. The shortest answer is that the equilibrium, you don't include them because their concentrations are fixed. The equilibrium expression, the law of mass action tells you, okay, at equilibrium, you tend to have a certain concentration of reactants or products over reactants. That ratio is equal to some particular value. So let me show that here. So like, for example, well, just very basically, concentrations of products over concentrations of reactants. And the idea is, okay, these reactants, these substances, their concentrations can fluctuate, they can change, but when they've reached equilibrium, their ratio is always equal to this constant that's characteristic of the equilibrium reaction that you're dealing with. Liquids and solids, though, have a fixed concentration. Their concentration is invariable. Yeah, invariant. Um, so if their concentration isn't changing, it doesn't make sense to need to include them in the equilibrium expression because the equilibrium expression is trying to characterize how the concentrations of certain substances does change depending on the state of the equilibrium. So that's the simplest answer. Basically, it's that we don't include them because their concentration is fixed, is constant. You can get a little bit more technical, and were exposed to this, maybe a little unintentionally. You were exposed to the idea in the reading that I submitted, or I assigned to you, about the concept of activities, and that technically the equilibrium expression should be written not in terms of concentrations or partial pressures, but in terms of activities, which is a general concept of how reactive something is. Activity increases with concentration and it increases with pressure. So we normally just substitute those in the first run general chemistry course. But technically, equilibrium constants, law of mass action is written in terms of activities. And the activities of solids and liquids are usually around 1. So they're essentially left out of the equilibrium expression. Their activities are fixed at 1. Is the Bronsted-Lowry definition of acids and bases the best definition? I would say there is no single best definition of acids and bases. I will say it is not the most refined definition. It is not the most modern definition. The modern definition, the one that is most, I guess, is considered the best in the sense that it is the most developed definition, is actually the Lewis definition. That's Lewis as in Gilbert Lewis, the guy who developed Lewis diagrams. So Lewis has his own interpretation of what makes something an acid or a base. In the Lewis definition, the Lewis concept of acid-base reactions, an acid is not a proton donor, but an electron pair acceptor. And a base is an electron pair donor. That is, I would guess, the most refined. I wouldn't say it's the best. I don't think there is a single best definition for an acid or a base. We will use all three of them at some point. Chemists will use all three definitions depending on the problem at hand. Sometimes if you're just dealing with a simple neutralization process, it's perfectly fine to think about it in terms of the Arrhenius definition. If you're thinking about reactivity, and other principles, like I give you one example that comes to mind, is like curdling milk. Curdling milk you can do with any acid, because what happens is the milk, the acids donate protons onto the milk proteins, and those milk proteins normally would have negative charges on them. Those negative charges allow them to dissolve into solution. You stick protons on there, you neutralize them, or you remove their charge, and then they all clump together. They won't stay dissolved in liquid with their negative charge. Instead, they gain protons, they become neutrally charged, and then they're dominated by London dispersion forces, and they all clump together into solids. So that's a case where I would argue it makes most sense to just think about it simply as a Bronsted-Lowry type definition. When you deal with more refined chemical reactivity, when you get into organic chemistry, you'll talk about, all right, how does one particular group attach to a molecule? Or how does one reactant attach to a molecule? How do bonds form? How do bonds break? Bonds form and break by sharing electron pairs or donating electron pairs, breaking electron pairs. So in that context, the Lewis acid-base definition is the best. So there is no single best definition for an acid base. There's just different definitions depending on the scenario. For the most part, in this section, we're going to focus on the Bronsted-Lowry definition. We'll be using that for most of our discussion. So there's that. How do you find K if no concentrations are given? You really can't. If you're not given any information about concentrations, equilibrium concentrations, or pre-equilibrium concentrations, you really can't calculate or determine the equilibrium constant. I'm sorry, I think about this mathematically. If you're trying to calculate a value, you have one unknown and you have only one equation. So you need to know something about these concentrations, which is normally going to be provided to you in some way. So if you're not given those concentrations, you can't calculate K. What complex does the HCl plus NH3 reaction form? It doesn't form a complex. It forms ammonium ions and chloride ions. So these should all be in, I guess, maybe not necessarily an aqueous solution, but the reaction that occurs would be this one. And in fact, I won't even say this has to occur in aqueous solution. It can happen in a gas phase as well. But in any case, it doesn't form a complex, it forms just these products, where the proton, hydrochloric acid acts as an acid, it transfers a proton to ammonium, so ammonia becomes ammonium with a net positive charge and leaving the chloride ion. Does how strong an acid is that based on intramolecular forces? So for example, HCl versus HF. HCl is a strong acid, this HF is a weak acid. Is that based on intramolecular forces? Intra being opposite to intermolecular forces. Intermolecular forces are forces between two molecules. Intramolecular forces are the forces within a single molecule. So you can imagine, like, this is the chlorine or the fluorine, and then this is the hydrogen. And short answer is yes, it's dependent upon intramolecular forces. If you have very strong intramolecular forces, meaning if you have a very strong bond between these two atoms, then they tend to not separate as much. So in general, yeah, the hydrogen fluoride bond is a stronger bond than the hydrogen chloride bond. There's a little more to it than that. It's not just about the properties of this single substance, it also depends upon what the proton is being donated to, but generally speaking, yeah, it's based upon intramolecular forces. I don't understand what you wrote when you had HCl subscript carbon tetrachloride. Why was it a subscript? Okay, that's actually a really good critique. I think I unnecessarily wrote that as a subscript. I shouldn't have done that as a subscript. I should have written it sort of on par with HCl. It should have been like this. It should have been HCl and then in parentheses carbon tetrachloride, lowercase, but not as a subscript. And that's analogous to if I were to write HCl in aqueous solution. The part about putting it in parentheses is trying to tell you, okay, what phase is it in? Is it in the gas phase? Is it in a liquid phase? Is it dissolved in an aqueous solution? In this case, the reaction I was talking about was saying this is HCl dissolved in carbon tetrachloride. So that one was specifically trying to show how hydrochloric acid could behave, react, and act as an acid independent of being in a water solution where it can generate hydronium ions. So that was that was the purpose of emphasizing that it's not in an aqueous solution. There's no water around, but it's in a different solvent. If the pH scale is based solely on hydronium concentration, why do we say that bases are characterized by hydroxide ion concentrations? So that's that. Okay, so that's working with the Arrhenius definition, and I would argue there's a couple ways you can express the Arrhenius definition of an acid and a base. I would say that there's multiple ways to express it. Like probably the most formal definition of an Arrhenius base is an Arrhenius base is something that decreases hydronium concentration. So how does that track with us? So an acid, according to the Arrhenius definition, an acid increases hydronium concentration. A base increases hydroxide concentration, but it does that by simultaneously decreasing hydronium concentrations. I will consider these two to be synonymous or essentially the same statement. The reason being that, okay, we already established here that in liquid water, you have this, which we call the autoprotolysis of water, where water will spontaneously transfer protons between each other and form hydronium ions and hydroxide ions. The equilibrium expression for this is that, okay, K is equal to concentration of hydronium times concentration of hydroxide. This product is equal to a constant, which is 10 to the negative 4. We sometimes call this Kw. It's the equilibrium constant, the dissociation constant of water itself. But the key point of this equation here that I will point out now is that these two quantities, concentration of hydronium and concentration of hydroxide, are inversely proportional to each other. So I know, okay, if I know the hydroxide concentration, I also know the hydronium concentration. They should always be equal to, or rather related to each other in this fashion. So we can talk about the pH scale and just talk about hydronium concentration, and then we can also discuss hydroxide concentration simultaneously because we know that they're going to be intimately related to each other. A base decreases hydronium concentration by increasing hydroxide concentration. If this goes up, that goes down. Last question. How can you determine how strong an acid is? Not easily, without any other information. I mean, there's two ways you can do it. One is that you can learn all the strong acids, and I would recommend that. You should. It's valuable to know the strong acids. I tend to not require that, but I think it's a valuable skill, and I might actually require people to learn them. I think actually take that back. I probably should require people to learn them. That's useful. So things like hydrochloric acid, sulfuric acid, nitric acid, chloric acid, hydrobromic, hydroiodic acid, those are all the strong acids. So you should know the strong acids. Now weak acids, you can also compare their relative strengths. And how do you determine whether something is a strong acid or a weak acid it's a little tricky to do, short answer. If you know the equilibrium constants, then you can say something. So the equilibrium constants, the Ka's, the larger the Ka, the stronger the acid. So basically any acid with a Ka greater than 1 will usually be considered a strong acid, thereabouts. Anything less than that is considered a weak acid. So if you have two acids, you want to compare their relative strengths, you need to know their Ka's. If you also think about the fact that the willingness of a substance to donate a proton is based upon the strength of that say, hydrogen. So if in the case of hydrochloric acid, the tendency for hydrochloric acid to separate is based both on the strength of that bond and the stability. Sorry, I'm running out of space here. It has to do with the stability of the product ion. So case in point, something like hydrogen, that's a good example here. Something like methanol. Methanol is CH3OH. CH3OH is neither strongly basic nor strongly acidic. It's not, even though you would look at the formula. I know I would look at the formula, I would see an OH and think, oh, it has OH in it, it's a base. Not necessarily. If it's a base, it needs to transfer, it needs to donate that hydroxide group, release that hydroxide group. And that's not going to happen because this carbon-oxygen bond is quite strong. So you're not going to just separate off that cleave that carbon-oxygen bond and get a hydroxide group. That's not going to happen. And in this particular structure, the hydrogen-oxygen bond is relatively, I'll just say relatively strong. Relatively. And furthermore, the product, this methoxide ion is not terribly stable. The oxygen there in solution at least, it's not terribly, in an aqueous solution, it's not terribly stable. It doesn't really want to exist in that form. So whether something is a strong acid depends both on how willing you are to break and lose the proton and how happy you will be without that proton. If you're very unhappy without that proton, then you will tend to gain it back and keep it, no matter how strong the actual bond there is. So the point being that there's two ways you can do it. One is by looking at Kas, and the other one is by sort of logicking to yourself based upon your understanding of chemical bonding stability. And that one is obviously much more tricky to do. So I won't be asking people to do that just yet. You will be expected to make those types of rationalizations when you get to organic chemistry. And you're assuming at that point that when you get into organic chemistry, you'll start to really get a sense for relative bond strengths. That's a big component in organic structure. Okay, that's all the questions for today. I hope everybody has a good weekend.